My topic today is in line of what Francis Sebera, my boss, has been presenting before, and it's just describing a little bit of what we're doing in the field of embedded machine learning, or EdgeML, as we just call it. And I will go a little bit more in detail about our use cases that we are currently doing in the field of rail. So just to be a little bit more specific on what is IoT and what are we doing in IoT, this is the traditional approach of doing machine learning in the field of IoT. So what we actually have, we have some IoT device, which is somewhere. We can put it, for instance, on a rail wagon or somewhere else. We connect it via our mobile net, different ways of connecting it, to the cloud where we have our IoT platform. And then we do machine learning there. So that's the traditional approach. And as you know, BigML is our tool that we are using for this challenges, and this is working very, very fine. We are doing now all this different analysis in the cloud, and provided the outcome of the machine learning models. We're doing the predictions there, and then use it for reports, for alarms, for applications, and whatever. So this works totally fine for most, or at least for many use cases. However, we see that within the IoT field, if it comes to machine learning, there's a new trend, and well, a new trend, but it's more challenging sometimes to deal with large amount of data. And what's actually happening there is that you have to think about some alternative, and the alternative is bringing the machine learning prediction on the IoT device. So I will more talk about this in the next 10 to 15 minutes. Which is basically where you're starting to get a loop here. So you're transforming that, you're getting the data, you're analyzing the data, you learn the models in the cloud. But once you have the model ready, you start to deploy the model back on the IoT device to do some more predictions on the device, and do not send all the data to the cloud and then do the analysis in the end in the cloud, but you just do the analysis already on the edge. So why is this necessary? Because IoT projects usually have some challenges. One of the challenges that we often see, this is the one in the middle, the bandwidth, the amount of data. So if you're aware of sensors, for instance, vibration sensors, you will realize that the amount of data can be really substantial. So or if you think about image data or video data, then you get a very, very large amount of data, which is in many cases not easy to transfer into the cloud, because there can be limitations in the bandwidth. There can be also costs associated. So cost is a big thing in IoT. I mean, for us, it's sometimes interesting, of course, to transfer large amount of data, but it doesn't make any, if for large for some IoT projects, the project is just not feasible if you have to transform that large amount of data over the mobile network to the cloud, because it's just too costly and there's no business case behind it. So you have to think about how to reduce the amount of data. Another aspect is also here mentioned, this latency. Imagine of autonomous driving, for instance. If you would have to transfer all the raw data that is collected by a car in an autonomous driving setting to the cloud, do the analysis there, do the prediction there, and then transfer back the actual actions that should be taken by the car, it would take far too long if the car is driving, I don't know, 100 kilometers per hour. So the prediction has to be done on the device in order to be quick. On the other hand, another important point is the power supply. Many IoT projects are lacking any power supply. In that case, we have to rely on batteries. And if it comes to battery consumption, IoT devices, for instance, on rail cargo wagons, this battery should last for years. Yeah, I don't know, for 5 years or for 8 years. And the most driver of energy consumption is actually data transmission. So you would like to reduce any data transmission that is not necessary. And for that case, you also have to think about what data you can process on the IoT device before sending it, because sending is energy consuming. And another point is also privacy. If you think about raw data, you do not want to send out any raw data, or in some cases, in particular if it's personal data. We have use cases that we're discussing with customers where I don't know, some employees are associated to IoT devices. I don't know. For instance, if a car is connected, then you do not want to see who is driving and where the car is driving, but you would like to see the status of what has been done with the car. Is it loading or unloading, or you would like to get the summary in the end. So this is the motivation of doing it, of doing EdgeML. And what it actually is, it's getting information from the IoT devices. You're running machine learning algorithms directly on low power and low cost microcontrollers in order to make IoT projects feasible. We are not the only ones who are thinking about this kind of these technologies. If you have been looking anytime in the past years in this Gartner hype cycle, then you would discover these little words, EdgeML or Edge AI or embedded AI, and they are kind of coming up on the edge. And we are now at the point where we are, at least also according to Gartner, getting to a point where this technology is kind of getting more and more mature. And we can see that that also our customers are demanding increasingly solutions related to embedded AI or embedded ML. And yeah, so this is a very interesting and fascinating topic. And for me, it's in the field of IoT. There's no way around it. We are not the only ones who are doing EdgeML. So the big companies, the tech companies, are using this already since a while. If you have such a sports watch similar as I do, then you probably realize that many of this data is already processed on the watch itself. So for instance, I have one and I can go swimming, and the watch is immediately detecting what kind of swim style I'm currently performing automatically. This is not done by transferring all the data into the cloud and analyzing it there and doing the predictions there. No, everything is calculated on the watch. And once you connect the watch again to the, I don't know, WLAN, then you will see that you will see the results of what you've been doing, your activities. So this is exactly what we are talking about. And this is a very, very nice application. Another thing is also Alexa, which is also not transferring all data in the cloud. Many of the processing is happening on the device itself. Or think about your mobile phones with image recognition to unlock your cell phone, for instance. This is also an application running on the mobile phone itself. What's the difference here? Here, the performance of or the controllers that are used are relatively powerful and expensive. So, and our motivation is to decrease costs here and to use really low power microcontrollers that are, I don't know, cost a few dollars, which actually make IoT use cases feasible in terms of business case. Yeah, so what is needed? What do you need in order to get into this field? Of course, you need machine learning. So we are doing machine learning, my colleagues and me, and we are also relying here on BigML, which is helping us a lot to be quick and to be efficient in terms of machine learning. However, we realized that it's not only machine learning that you need in order to be here successful. You also need embedded software engineering. In that case, we are happy to have our team supporting us in this field. And what else you need is you need some feeling and some experts in IoT solution design. And this is also something that we are combining in our company. So we have been able to work on this field over the past 2 years about. And what we found out is that there's a chain that has to be followed, and the chain is basically something that is a mixture between machine learning and data analytics, as well as embedded software development. It all starts with data capturing. So you have to find a way how to capture your data, and that sounds more easy than it actually is. Because imagine if you would like to understand if some device is experiencing some damage because of shocks or whatever, then you have to do experiments. So I will come to this point later on in the rail presentation, the rail part. But data capturing is something that you have to learn how to do it, and we had to make our own experience with it. Data processing is something that is relatively straightforward. So you know this feature engineering, this is what you're doing. Model training, evaluation, finding the best models here. Thank you very much. We can rely on BigML. We're using this heavily, and we are using various tricks and support from BigML to actually get to small and exportable models. And the next part, once you have the models, is then to think about how to bring the model on the IoT, on these IoT devices, on the microcontroller. This usually involves some kind of conversion of the model into some code, into C code, for instance, or C++ code that can run on the IoT device. It also means that all the data processing steps and the feature engineering steps have to be duplicated, so to say, on the microcontroller. You have to think about how you do this on this target platform, and also, and I will not go too much in detail about this, how to connect the IoT device to the cloud. Because in the end, what you actually would like to see, you would like to see that you can update your model over the air. You do not want to go to this IoT device and plug in something. You would like to update the model. You would like to evaluate the model. You would like to see if the model is really performing well. And if not, then you can update it and deploy a better model over the air. So one use case, or the most prominent use case that we're currently working on, is the one about damage detection. And this picture that you can see here is actually more or less describing the use case that we're working on. You see here a rail wagon, and what's our customer, the Austrian Railways, are doing is they are renting out these rail wagons to customers. For instance, they can be in the forestry industry. And here the problem is that there's a lot of physical shocks happening on the wagons. And if you imagine these wood logs falling down on the wagons, for instance, then you can probably imagine that something can break here. And this is actually what they would like to detect. And this is a very important topic for them, because they have a lot of costs involved with maintenance and to repair these wagons. And they would like to understand what is happening, where it is happening. Sometimes the wagons need to get stopped on the way from A to B because they are broken. So this is very expensive, and they would like to understand what's happening there. And further on, it's also interesting to get information about the health status of wagons. So what we actually did, we started with a small POC, and this did not involve EdgeML at the beginning, but we started to collect these various shocks from the IoT devices. So where did we get this from? We had a previous large IoT project together with the same company, where we have about 15,000 wagons connected with IoT devices that already have some acceleration sensors and gyroscopes on the devices. So we received this kind of data, and we received the information about any shock that is happening there. So what else we need to do is we had to find out if a wagon is broken or not. So we also got this information, and what's actually the target. What was the goal that was coming from our customers, to identify which customers are causing damages, more or less, and to understand any kind of patterns that are lying behind this acceleration alarms. In this experimental setting, we had to look into the damages. It's not so straightforward to understand which wagon is not damaged, and not because there are so many damaged wagons, but we haven't had information about a wagon that is not that is actually okay. So we decided to differentiate, to take only wagons that have been identified or that have been observed by the wagon master, as it's called. And the wagon master can identify heavy damages. This is just an illustration of the picture, but it can be, for instance, some wood logs falling down and breaking some of these these metal things here, and then there are small minor issues. And we assume that if there's a minor issue, then recorded, then there's obviously no bigger issue recorded. So we said, okay, all these wagons with some minor issues are more or less okay and not damaged, and the other ones are damaged. And then we have been using information about the shocks, and I can go into this more in detail if you would like to in a separate session, but there has been, we worked with very detailed sensor data, and we created features out of this data that has been collected over about, I think, 4 months or 5 months. And based on this, we created these kind of features that you can see here a little bit. So it's more or less some kind of statistical descriptions about this time windows that we have selected. We collected information about the wagon type and also about the customers. And then we've been running this model in BigML. We used AutoML to look for the best models that are available. And we finally came to the point, and this was at that stage really some surprise, that we can see that we really find a very high correlation between the shocks, the physical shocks happening on the wagons, and some kind of damage that has been detected by the wagon masters. So the precision was more than 95%. And this was the basis actually for the next project that we've been starting, that we're currently working on. And this project is now getting far more in detail than what we've been doing in this first POC, because what we're now doing is actually not just saying, okay, well, there's some connection between damage, between some shocks, physical shocks, as well as some damage. But now we would really like to understand which shock is now leading to which kind of damage, or at least to some damage. And by doing this, this gets far more easy, because now we have to go more in detail if it comes to the data. We are not just using if there's been a shock and just using the amplitude of the shock, but we are taking much more detailed information about the shocks. And this means that if there has been a shock, then the data is collected in a very high frequency. So it's not just one point, it's a lot of data that is collected by the acceleration sensor. And we would like to need this data. And in order to work with this data, we have to do some kind of pre-processing, which is actually running an algorithm on the IoT device that is located on the wagon itself, because IoT devices are running on battery. And as mentioned before, they should last, I think, about 5 years at least, or up to 8 years. And it's not feasible to transform all this large amount of data over the air, over the mobile network to the cloud and analyze it there. No, we need to analyze it on the device. And this is actually the challenge that we're currently working on. In the end, the settings should look like this, that you have the device, you have the algorithm running. The algorithm is obviously calculated and developed, or the machine learning model is developed in the cloud. Once we know the model has to be reduced and quantized, as I say. In terms of, in case of BigML, we are trying then to find the smallest possible model, which is still achieving some high quality in the evaluation. This means, for instance, creating one high-performing decision tree that is exportable, translated into some C code, to the deployment over the air to the IoT device, and there let it run. And what you would like to have in the end, there's only an event notification and no transfer of large amount of data. This is not the only use case that we're working on. The other use case that we've been also working on, this is something that Francis has been mentioning before, is in the field of energy supply. So we are talking here about pantographs. Ironically, there is a lack of power supply on pantographs. Why? Because the voltage is far too high for any microcontroller. So you also have to rely here on battery supply. And again, you have exactly the same problem where you are using acceleration data, which should be a proxy for understanding the pressure of the pantograph that is on the infrastructure. And this is very important for for various stakeholders. So it gives information about these elements that are worn out on the that are currently, they're moving here, and you have to replace them. Secondly, it also gives some indication about some problems, as you have been seeing in Francis' video, or it can also give you some indication about the quality of the infrastructure. Another use case that we are also working on with our partners are to identify the weight of a wagon. So it's about loading. Is the wagon overloaded? Yes or no? And to what extent? Because there are automatic loading sensors which are run by the infrastructure providers, and they are identifying relatively easy if a wagon is overloaded, which is nice for them, but it's not so easy, not so nice for the operators, because if their customers are overloading the wagons and the overloaded wagon is then running into this checkpoint, it means that you have to pay some penalty, which is costly and very inconvenient, because it could also mean that you have to put one of the wagons out of the entire train, which takes time, and is also involved with, also leads to a lot of costs. Again, here we have some kind of sensors. In that case, it's an infrared sensor, which is measuring the distance between the axis and the wagon. And this is not a one-time measurement, because a wagon with this with the suspension is constantly moving. So you cannot take just one value and say, okay, this is, I don't know, 13 centimeters, and then it's done. No, you have to do a lot of calculations, which is some kind of calibration in the end. And based on these different values, you can then calculate you can identify if there's some overloading. And how to do this, the best way to do this is also to do it with some machine learning model. And another project that we have doing is also with flat spots. In that case, a flat spot in the rail industry means on the wheel there's some spot which is not totally, the wheel is not totally round. You have some spot which is flat, and this means that if the wagon is then running, there's some constant vibration and pressure, which may destroy, for instance, part of the axis or other part of the wagon. And this is the nightmare for the people in the rail industry. So what they would like to understand is they would like to identify as soon as possible if there's a flat spot. And the flat spot is detectable by using vibration sensors. So actually, it's also an acceleration sensor. So you see this vibration, and based on this vibration, which is a time series with some very high granularity, you can then identify if there is a flat spot or not a flat spot. Again, you do not want to send all this huge amount of data constantly in the cloud, because it's far too costly, it takes too much battery, and doesn't make any use case possible in the end. So what you would like to do, you would like to do this constantly, run a model on the device and understand if you have some indication for flat spots, and if yes, then you would like to send a notification to the controller and send, okay, attention, there's an alarm, maybe there's a flat spot with some, I don't know, 75% probability. This is actually the goal. Yes, so that's the project that we're currently working on. If you would like to know more about it, or if you would like to ask some questions, we are very happy to talk to you about this.